All right, let's move into section 4.6 on linear approximation and differentials. This is kind of useful. The differentials is going to be useful whenever it will evolve into integration a little bit. But this is also a good tool to use in order just to approximate some values, because when you look at it, this picture that we have here is kind of zooming in on a certain point, and what happens instead of having this, as we zoom closer, you get a good approximation on the line that is tangent to that curve at that point. That is very, very, very close to the actual function value there is for point P in this case. So imagine plotting a smooth curve with a graphing utility. Now pick a point P on the curve, draw the line tangent to the curve at P, and zoom in on it several times. As you successively enlarge the curve near P, it looks more and more like a tangent line. This is this fundamental observation that smooth curves appear straight on small scales is called local linearity. It is the basis of many important mathematical ideas, one of which is a linear approximation. So, given the following graph, we can write the equation of a tangent line to the curve and use that to approximate values of a function. So I'm going to create a graph here for you. And we have some function f, does something like that possibly. So this is y equals f of x. Then I'm going to create a tangent line, say it right here. So it would be intersecting just at one spot. And I'm going to call that point A, and I'm going to call this would be the corresponding f of A value for that. And I'm going to let y equal here L of x represent the line that is tangent to that curve at that point. Now, what do we know about the point, the slope, of that tangent line, L of x? So, slope of L of x. If L of x is a tangent line, and I'm asking for the slope of that tangent line, hopefully, that reminds you of the derivative of our function, and in this case, we're doing it at the point A. So I'm going to write that as f prime of A, and the point that I'm looking at is f, or A, comma, f of A. So if I'm writing the equation of a line, I need a slope and I need a point. So I'm going to write the equation of that line given this point and that slope using point slope form. So going back to old school, y minus the y value equals our slope, which is f prime of A, times x minus the A value, or x minus the x value that I have in my point. Now, I could have the audacity to solve this for y equals. So I'm going to add this piece over and say y equals f of A plus f prime at A times x minus A. And that right there is what I'm proving to you to be what they refer to, as L of x. The linear approximation. So here's the formal definition that we have from that. Suppose that f is differentiable on an interval I containing the point A, then the linear approximation to f at A is the linear function L of x equals f of A plus f prime of A times x minus A for any x in I. So what we are approximating is going to be our x value. What the nice A value is that we are picking is going to be kind of the nicer whole number there. So we're going to use that linear approximation to find an estimate for f of, or you could do f here, L of 5.1, given that f of 5 equals 10 and f prime of 5 equals negative 2, okay? So, just so you know, this, remember, is going to be our x value. Our A value is kind of the nice point that we know more information about. Therefore, we're going to look at f of 5.1, which is the same as L of 5.1, just a notation deal, is going to be f of A, so we're going to choose f of 5, add to that f prime of 5 times our x value that we're looking at, which is 5.1, minus that a value, which is 5. And from here, I'm going to plug in values and figure out what it's equal to. So L of 5.1 is equal to f of 5 is 10, plus, here we have a slope of negative 2, times this, when I subtract, becomes a 0.1. So 10, this ends up being a minus 0.2, ends up with a value of 9.8. So here, we don't really have any way we can compare things to just because we don't know what our actual function is, but our approximation for f of 5.1 using things around x equaling 5 or a equaling 5 is going to be at 9.8. Okay? All right. So, what about finding a linear approximation to the function at a given point A? Okay, so here we're just going to write the equation of a line. So, what do I need for that line? L of x is equal to f of A plus f prime of A times x minus A. So, let's figure that out. Let's figure out what f of 1 is in this case. If I throw 1 into here, times 5 is 5, minus 1 is a 4, so I get the square root of 4, which is actually 2. Now, I also need to know what the f prime of 1 is as well. Well, that means I now have to take the derivative of this function. I'm going to write this function as 5x minus 1 to the 1/2. And I'm going to bring my 1/2 out front, decrease that power by 1 using my chain rule, and then take the derivative of the inside, which is a 5. So if I want to rewrite that, then I could write that as, I'm going to put 5 on top, the 2 would be on bottom, and then this 5x minus 1 to the 1/2, or the square root of that, would be what I have. So now whenever I determine what f prime of 1 is, I have 5 all over 2. When I plug 1 in here, times 5 is 5, minus 1 is 4. The square root of 4 is 2, so I end up getting a 2. Therefore, my slope is 5/4. So now, can I use that to write the linear equation? Absolutely. L of x here is equal to, now you can change each one of these to the 1 if we want, because that's our a value. So f of 1 we found was 2, plus f prime at 1 is 5/4 times x minus 1. And now it's just simplifying that right side. So I get, when I distribute my 5/4, I get 5/4 x minus 5/4. Then I have to combine my 2 and my 5/4. So I'm going to rewrite the 5/4 x to come out front. Then I need this to be over 1, so 2 over 1 minus a 5/4, so I need a 4 and a 4. So 8/4 minus 5/4 looks like a 3/4 as my final answer. And that's all they're asking for. When they ask you what's the linear approximation in generic form, that is what it is, okay? Same thing you're going to do here with these two problems. We want to write the equation of the line that represents the linear approximation. Then we're going to use that to approximate the estimate for what we are asked for, and then we're actually going to calculate a percent error. So how close are we when we do this type of approximation? So for part A, we're going to write our equation. A is equal to 1. So f of 1, 6 minus 1 minus 1 squared. If I do that, I get a 4. Then I have to determine what is the derivative of that function to determine what f prime of A is. So if you want to write this right here, here's the linear function that I'm going to be writing from our definition. The derivative of this function is 0. Then I have a negative 1 minus a 2x. And so that is what I need to throw my A value into now to find f prime at 1. So when I do that, I get negative 1 minus 2 times 1, which actually is a negative 3. Okay? So what is my line? What is my L of x? L of x is equal to f of 1, which is 4, plus my slope, which is a negative 3. So actually, if we want to undo that and do a minus 3, times x minus the A value, which is 1. And I'm going to simplify that by distributing. And I get 7 minus 3x, or minus 3x plus 7 as my L of x. So that is part A. That's the equation that we have. Part B says, though, I want to use that to find the approximation for my function value at 1.1. So I want to know what L of 1.1 is of doing 7 minus 3 times 1.1. And when we do this as a negative 3.3, 7 minus 3.3 actually gives me a 3.7. So this is actually my answer for the approximation for 1.1 on that given function. Now, part C asks us to compute the percentage of error, which means I'm going to take 100 and then do the approximate minus the exact and divide that by the absolute value of the exact, where the exact value is given by a calculator. So this is where you want to plug in the 1.1 in for x and do 6 minus 1.1 minus 1.1 squared. So we're going to start with 100. Now, the approximation that we found was 3.7. So I want to do 3.7 minus. When you plug in 1.1 into the original function, you will get 3.69. That is what I want to then divide by 3.69. Now, all these are in absolute values, so if you get a negative, just disregard that. So when you do that, make sure you subtract here, divide by this, and then times by 100. I will tell you that the percent error that we have for this problem is 0.27, which is very, very, very small when you're looking at approximations. Okay, so it's a good answer for the actual answer for 1.1 into that function. Okay, so let's do the same idea with this next function. A derivative here is just a little bit nastier than the one before. So on part A, our A value is 0. So let's figure out what f of 0 is. When I plug 0 in here, plus 1 is 1. 1 to any power, I don't care if it's negative or positive or what number it is, it's still going to be 1. Then I have to define the derivative of that function. So we're going to do a little chain rule, do a negative 1/3 out front. 1 plus x, don't change that. Decrease this power by 1 by subtracting by 3/3, which gives me a negative 4/3. And then I have to take the derivative of the inside, which is just a 1, so I'm not going to write that per se. And now I need to find what is f prime of 1, or f prime of 0, excuse me. When I plug 0 in here, I get 1. Again, 1 to any power is going to be 1 times a negative 1/3 ends up with a value of negative 1/3. So now I can find my L of x, which will be my approximation. So I'm going to do f of 0, which is 1, and then plus the slope, which is negative this time. So I'm going to go negative 1/3 times x minus the a value, which is 0 here. And that's awfully nice because I don't have to worry about simplifying anything here. When I do 1 minus 1/3 x, then I get a 0 for the next one. This is actually going to be my equation. Now, you could write that as negative 1/3 x plus 1. That'll work too. Either way is acceptable. You just have to make sure you realize that they are equal in a multiple choice situation when you're working in my lab math. All right, part B. We now need to use that linear approximation to determine what is f of negative 0.1. So L of negative 0.1 is a good approximation for f of negative 0.1, and I'm going to plug that into here. So I do negative 1/3 times negative 0.1, and I'm going to add 1. Now, when you do that into your calculator, I would suggest that, you're going to end up with a 1.03 repeated. Okay? All right, so that's part B. That's the approximation for it. Part C wants to know how close that is to the actual. So we're going to do 100, and we are going to times that by taking the approximation minus the exact. So 1.03 repeated. And when you plug in negative 0.1 in for this function, I will tell you this is what you get. And I wrote it all out just because I don't like to round too early. 1.035744169 in absolute value. Divide that by that same exact value. And I'm going to end up getting, and this should be an absolute value, sorry. When you do that, this minus this, hit equals, divide by this, hit equals, times it by 100, gives you a percent error of 0.23. So very, very close to what you had before, but you're still able to do that. Okay? All right, so now let's use this linear approximation to find some values for some of these functions. And so we're going to have to display what is the function. We're also going to have to end up being able to find out what the final answer is on that. So here, use linear approximations to estimate the following quantities. Choose a value of A to produce a small error. So notice I have 1 over 51. I'm going to model that function as 1 over x that we're working with here. I'm going to write that as x to the minus 1 for my derivative purposes. I'm going to choose A to equal something close to 51. I'm going to choose 50. So what I'm out to find is what is f of 51. That's the actual one, but we're going to use a linear approximation for that. So I'm going to find out what is f of 50, and in this case it would just be 1 over 50. I now need to find out what is the derivative so I can find f prime of 50. So I'm going to multiply out front, gives me negative 1 x to the minus 2, which is the same as negative 1 over x squared. So therefore f prime of 50, when I plug that in, gives me negative 1 over 2500. And now I can find that linear approximation. So I'm going to do L of x. We've done that already before. Take f of 50, which is 1 over 50, plus the slope that's negative. So I'm going to go negative 1 over 2500 times x minus the a value, which is 50. So I will tell you that when you distribute that through, you end up getting 1 over 50 minus 1 over 2500x plus 1 over 50. And when you add 1 over 50 with 1 over 50, I'm going to keep the x term, negative 1 over 2500x, and then I get 1 over 25, and that is my linear approximation. So you have to go through the process of writing that linear approximation, and now to answer the question, what is the approximate value of that? Now I get to throw in 51 into that approximation. So I get negative 1 over 2500 times 51 plus 1 over 25. And again, a lot of calculator work here. I will tell you that that comes out to 0.0196, which is also the same as 49 over 2500. So either one of these answers will work. Depends on if they want an exact answer, if they want an approximate or a decimal answer. And my lab math would be the only difference there for that. Okay? So this next one I wanted to show you as well. Just again, identify the function. This time I have a square root, which is the same as x to the 1/2. I'm going to choose something nice for the square root for my a value. And notice that I have a perfect square at 81. So I'm going to choose a to equal 81. And what we are looking for is, what is f of 82? That's what's in question. So again, I need to determine what is the f of 81, which means I throw it into here. Gives me the square root of 81, which is 9. I need to find the derivative of my function to determine what is the slope. If I bring the 1/2 out front and decrease that power by 1, I get 1/2 x to the minus 1/2, which is the same as 1 over 2 square roots of x if I bring that negative exponent to the bottom. Therefore, evaluating at 81, I get 1 over 2 square roots of 81, which that is 9, times 2 gives me 1 over 18. So, just as before, here comes that linear approximation. I'm going to take f of 81, which is 9, add to that my slope, 1 over 18 times x minus the a value, which is 81. So, when I distribute and simplify, so you can kind of try to do that on your own. You can pause the screencast to see if you get it right. That would be 1 over 18x plus a 9/2, and that's my linear approximation. So The final thing that I have to do is to plug in 82 here. So I would want to know what L of 82 is and take 1 over 18 times 82 and add to that 9/2. Again, it will be very nice for you to use your calculator. You can get a fraction answer to it as well. I will tell you that the decimal approximation for this one is 9.05 repeated. And that would be our answer for the approximation of the square root of 82. Okay? All right, very good. Let's move on to concavity. Linear approximation and concavity. Additional insight into linear approximation is gained by bringing concavity into the picture. According to pictures, which situation underestimates or overestimates the actual value of f at a? So I'm going to draw a picture here, and I'm going to have a function that is concave up. And I have a point at which I'm drawing that linear approximation tangent. For concave up, what do I know about the line L? If this is L of x, it lies above or below that function. Well, in this case, L lies below f. And if L lies below f, then L is an underestimate. It is not as big as the actual function, but it is below there, okay? So if I then choose to do a function that is concave down, let's say, and I choose a linear line, that one's a little bit off, sorry about that, call that L of x, or L. In a concave down situation, then L lies above f. And if it is above f, that means that L is an overestimate of f. Okay, so concave up, underestimate, concave down, overestimate. And so find the linear approximation L for the function f at a. State whether the linear approximation is an underestimate or an overestimate of the function at a, and compute f double prime to confirm your conclusion. All right, so if I look at this equation, 10 minus x squared, that is a parabola where I'm intersecting moved up 10 and going downward. And so at a equaling 3, say it's something here, I'm going to have a linear line there. So at this case, and it is a concave down situation, I'm going to guess that we have an overestimate of our problem. Now, what is the linear approximation for that? Well, we have to determine what is f of 3. Plug in 3 squared is 9, 10 minus 9 is 1. What is f prime of our function? That's a nice easy one. It's a negative 2x, so therefore f prime at 3 is a negative 6. And so, writing my linear approximation L of x, I need my function value plus the derivative, which is a negative, so plus a minus 6 times x minus the a value, which is 3. And when I do 1, distribute the negative 6, we get minus 6x plus 18. Therefore, we get minus 6x plus 19 as our L of x. That's our linear approximation, so make sure you're able to do that. We've said it's an overestimate kind of from the idea of our graph, but does our second derivative tell us that? Well, if I now take the derivative of our function, our second derivative of our function, take the derivative of this gives me a negative 2x. What do we know about the concavity at 3? At 3, it's going to also be negative 2, and since that is negative, that means we are concave down, which means that we do have an overestimate of our graph. Okay, so I just wanted to show that to you a little bit as one type of problem. So now we're going to evolve into the idea of approximations, which actually evolves into the idea of differentials, okay? So I'm going to give you that linear approximation. Instead of L of x, I'm going to use f of x this time, is approximately the same as that linear approximation definition that I gave you earlier. So f of a plus f prime of a times x minus a. Now, where a is fixed and x is a nearby point, we can now rewrite the function above as simply by subtracting this over that f of x minus f of a is approximately f prime of a times x minus a. So just using a little bit of algebra here, okay? Now, when we talk about change in things, here, a change in something means I have to take the difference of that. For a change in from 3 to 7, it is 4 because I take 7 minus 4. So this should look like a change in our y values, okay, between x and a. This is a change in our x values between x and a. Now, in math, a lot of times we will use a symbol, a Greek delta, to denote change in something, and in science they use it quite a bit. So in this case, if I have a change in y, I'm going to write that triangle y to represent the change in y is approximately the same as this derivative f prime of a times the change in x, which I could recognize as delta x or the triangle x. Okay, now why is this important? This is going to, again, kind of lead us into what we refer to as differentials, not differentiables. Differentials. So, to approximate the change in y in a dependent variable when the independent variable x changes from a to some a plus delta x. Remember, that's a change in x. A is along our x-axis. One must calculate that the delta y is approximately the derivative at a times delta x. And we kind of have an application, a couple applications here for that. We want to approximate the change in y, which we can refer to as f of x as well, into this function when x changes from 1.0 to 1.05. So I need to know what the change in y is in regards to the first derivative at a times delta x. Now a is the place that kind of where we start, and this is where we're going to. So, a is equal to 1.1, a plus delta x equals 1.05. So we're changing from 1 to 1.05. Now, how do we determine our change in x? Well, if these are my x values, to determine a change in x, I got to take the difference of those two. 1.05 minus 1, which is 0.05. Now, I need that to throw that in for delta x. But I also need the derivative of my function and evaluate that at my a value of 1. So let's do that over here. F prime of x, in this case, is going to be 9x to the 8th minus 2 when I take the derivative of that function. F prime at 1, when I throw 1 into that function to the 8th is 1 times 9 is 9 minus 2, gives me a value of 7. Therefore, for this problem, the approximation is going to be 7 times 0.05, which is 0.35. So the change in the y value with a change in my x of 0.05 yields 0.35 as the change. Okay, so let's do kind of an application. Approximate the change in the surface area of a spherical hot air balloon when the radius decreases from 4 to 3.9. So we go from 4 to 3.9. To get our delta x, I have to take 3.9 minus 4, which is negative 0.1. Remember, a is where, we are starting from. So, we have to know what the surface area of a sphere is. And sometimes you may have to go back and refer back to some geometry formulas to help you out. So, the surface area of a sphere is 4 pi r squared. So now we're in terms of A and R. So if I want to find the change in A, I have to do the approximation of A prime at A and times that by our delta R. Okay? So actually I could refer to this as my delta R if I want to think of it that way as well. Okay? So what is the derivative here of that function? So change in A is approximately, I'm going to take the derivative, bring the 2 out front, gives me an 8 pi, reduce that power by 1, gives me an r. Remember, pi is just a constant, so it doesn't change, times delta r. And now at this point, I kind of plugged in over here. I can plug it in all at the same spot. So, we have delta A is approximately 8 times pi times the r value that I'm starting with is the same as the a value, so we have 4 times a negative 0.1. And if you run that through, it's negative 3.2 pi, but multiplying by pi gives you a decrease here, a negative of 10.05. So, and this would be meters squared. That's the change in the area given a change in the radius. So if we decrease our radius by 0.1 meters, then the surface area is going to be decreasing by negative 10.05. That's what we approximated with our variations that we have here. Okay? All right, very good. Last page. Last page is working in the differentials idea. Now, we will now introduce an important concept that allows us to distinguish two related quantities. The change in the function of y equals f of x as x changes from a to a plus delta x. That's what we were just kind of doing. We call that delta y. That's the change in the y. Now, the change in the linear approximation where y equals L of x as x changes from a to a plus delta x, which we can refer to as a differential dy. And that's the idea that we're going to get into, that differentials are now defined for this idea and for the next big idea in calculus, which is integration. The differential dx is simply the same as delta x. The differential of dy is the change in the linear approximation. We can call that delta L or delta y. And so we can kind of revert back. It's a notation thing when they revert into differentials and changing from the change of x to dy or dx and the change of y into dy. So here's our definition. And it's a pretty easy concept once you kind of get the definition. Let f be a differentiable on an interval containing x. A small change in x denoted by the differential of dx. And the corresponding change in f is the approximated by the differential of dy. Okay? Now, that dy is defined to be f prime of x times dx. Now, that's very similar to what we had before on the change in y. This, we had delta y is approximately f prime of a times delta x. We've changed the delta y to dy, changed the delta x to dx, and the derivative kind of stays the same. We are going to leave these values kind of in a variable sense, and then we'll kind of talk about an actual value at the very last problem. So consider the following function and express the relationship between a small change in x and the corresponding change in y of this form. So basically what I need to do from here, first I want to write that as x to the minus 4. I need to find out what f prime of x is, and then I attach it with a dy and a dx, and I'm done. So if I take f prime of x, bring this negative 4 out front, and decrease the power by 1, I get negative 4 over x to the 5th. And that is what I'm going to plug right in here. So therefore my final answer for this is dy is equal to negative 4 over x to the 5th dx. And that's going to represent the change in the y for every change in x, multiplying it by negative 4 over x to the 5th. When I have a trig function, haven't seen these in a while, take the derivative of that. You got to make sure you remember your trig derivatives, and the derivative of secant is secant tangent. Once I have that derivative, then I plug it right in here, and my differential dy is equal to secant of x tangent of x dx. And that's my final answer. So those actually kind of are nice and pretty easy as long as you know how to take those derivatives. But what does it help us with? Interpreting the results for that function 1 over x to the 4th. For a small change, dx in the independent variable x produces approximately change in the variable of dy in the form of negative 4 over x to the 5th dx. So if f increases from x equaling 2 to x equaling 2.1, what is the approximate change in the function? So basically what I'm asking for, what is dy? That's what I'm looking for. Now here, dx is the change in x. So dx is going to be defined by taking 2.1 minus 2, just like when I did the delta x. So dx is equal to 0.1. And so now, basically, I'm looking for this piece, for that specific function. dy is equal to negative 4 over, now what was x? X was 2 to the 5th power, and multiply that by my 0.1. And when I do that, 4 over 32 times 0.1, you will get a decimal value of negative 0.0125. So when there is a change in my x value of 0.1, there is a change in the function value or the change in the y value of a negative 0.0125. That's what we are looking at, and it's a decrease in the y because of the negative. Because of the negative, okay? All right, very good. So that's what we have in section 4.6. We are actually it's kind of its own little section in a sense until we get here to the end where we are evolving into some of the concepts which we'll look at in section 4.9. The next section, just so you know, is going to go back to a little bit of limits, but involving limits and derivatives. So that's kind of a little different section. And so we will see that soon. So until next time.